Thank you so much for the warm welcome. My name is Rebecca Nunu, and I'm a principal geoscientist at the Edwards Aquifer Authority. I'm from good old San Antonio, and I'm so glad to be here today to tell you a little bit about our work in identifying source areas to springs in West Texas. This is a story we've been building for the last couple of years, and the work I've done with my colleagues Ron Green, Paul Bertetti, Gordon Whitmire, among others. So at Southwest Research Institute, so thank you. And so before I get started, I want to give a few acknowledgments and thank yous to a number of groups and people that have made this work possible. We began working out here thanks to a seed grant from the Big Bend Conservation Alliance, and our work evolved over the years through the help of 2 research grants from Southwest Research Institute. And so as we continued to push this work forward, it was made possible by the help of our groundwater district managers like Greg Perrin and Ty Edwards from Middle Pecos, who were instrumental in helping us access sites and wells and springs and helped pay for samples. And really, they were our water champions, and they still are. As he alluded to just a moment ago, we were able to continue our work out west through the help of a U.S. Bureau of Reclamation Water Smart grant. And so alongside the groundwater districts and the Nature Conservancy and the Horizon Foundation, we've continued this work and we've extended it to Fort Stockton as well. So today's message is a success story for the kind of work we can do when we have buy-in and cooperation and support from landowners and districts and all the people out west. So thanks again to all of these groups. So increasing demands and limited supplies present severe challenges to many parts of the world, and Texas is no exception. There was an alarming statistic that came out that basically states that since the 80s, the number of springs that have gone dry has tripled, which is really alarming as it is an indicator of how our demands on groundwater have risen over the years. And so Comanche Springs is sort of an example of how the dynamics and the character and the flow of our springs have changed as these demands have grown. So what was once an oasis in the desert, as pictured above, is now a spring that only flows during certain parts of the year. And so springs in West Texas are particularly affected by a statistic such as that because, as Greg berated me just a moment ago, we don't get a lot of rain out here. And so pictured here is a map from El Paso to Crockett County. We're situated in West Texas, and our spring locations are the blue circles. And so our groundwater conservation districts are in the colored areas, and the groundwater management areas are outlined in red. And so as we know, groundwater and political boundaries are never the same, or often not the same. And some of the larger aquifer systems that are complex and feed these springs span across multiple districts and GMAs. And so some of those larger springs include Caroline Springs over at Independence Creek Nature Preserve, Hot Springs at Big Bend National Park, Diamond Y, Euphrasia, and Cargis Springs in Fort Stockton, and San Solomon Springs, otherwise known as Balmorhea State Park in Balmorhea. And so we're going to talk today about San Solomon at first, but the takeaway is that in order to tackle any of the water challenges out here, it requires the cooperation and working together amongst these different groups and landowners. So San Solomon Springs is a multi-outlet spring system with uncertainty in the sources that feed each of its 6 springs. I'm sure many of you here know that these springs are the lifeblood of Balmorhea and the surrounding communities. They provide for agriculture, water supply, tourism associated with the state park. In essence, they're a regional icon. And so there are 6 springs that form this spring system, and there still remains uncertainty into the ultimate source areas for each individual spring. And so numerous studies have been motivated to better understand better understand the complexities of this spring system as spring flows have diminished over time. So, as I mentioned, there are 6 springs. They include San Solomon, Giffen and Phantom, Saragossa, East Sandia, and West Sandia springs. And as you can see here, this is a box plot of total dissolved solids concentrations for the 6 springs. And as you can see, there are differences that are readily apparent. More specifically, Giffen, Phantom Lake, and San Solomon have similar ranges in median TDS values. East Sandia and West Sandia springs have elevated total dissolved solids that don't really overlap with our other springs. And Saragossa spring has a lot more variability and also much lower TDS values than the rest of our springs. And so as I mentioned, there remain uncertainties in better understanding what contributes to these differences. And that's what we're going to talk about today, is trying to better understand what might be contributing to these differences. So we at Southwest Research Institute embarked on a different approach to help tackle this problem. We combined hydrogeology with geochemistry and statistics into a tool that we call a geochemical framework. And so this geochemical framework is a structured approach that relies on the collection of robust geochemical data, robust in the sense that you're collecting a broad suite, a lot of geochemical data over a broad spatial extent over an extended period of time. And then we use those robust geochemical data and apply geochemical and statistical methods and hopefully end up with a refined conceptualization of our hydrologic system, a better understanding of where recharge is coming from. Are there differences seasonally? Using the geochemistry and employing this kind of framework can hopefully help us end up at a better understanding of our system. And so this is a really effective approach because we're using as much data as possible in order to highlight what are sometimes very subtle differences. But those differences can be important in delineating and understanding what's happening in our system. So in 2019, we started by sampling the 6 springs in Balmorhea and combined those new data with historical data. And so this is what my office looks like when I'm out in West Texas. So here are the 6 springs from right to left, or left to right: San Solomon, Giffen, and Phantom Lake. These are typically bigger, or they're not typically, they are bigger than East Sandia, West Sandia, and Saragossa springs. And so through the years, we've been able to expand our sampling all across the region to hopefully pinpoint different sources and understand what's going on. And as you can see through time, the locations and the area that we've been able to sample has extended further northwest. So our early results guided additional sampling, and so we were able to target what we hypothesized to be our source area, or that flow path that we thought or hypothesized to be feeding the springs. This wasn't always ideal. Well use has changed. Landowner access or land access wasn't always feasible, but help from Greg and Ty and landowner cooperation, we were really successful in being able to collect 48 samples from 7 springs and 15 wells. So, what do I mean by employing a geochemical framework? So this is a score plot, and this is what I mean by combining our chemistry and statistics. This is the result of something we call principal components analysis, or PCA for short. And so, in summary, PCA allows you to take a large number of variables, so in our case, that's our geochemical data, and combine them into a smaller number of grouped variables, which are our components, so that we can take a look at everything at once. We can really see the big picture in one step. So with our data, most of the variability that exists in our data is driven by our major ions, so think calcium, magnesium, potassium, whereas our second component is driven by silica and nitrate. And so we can also start to parse out different characterizations by quadrant, for example. So if you recall the TDS box plot that I showed previously, differences were apparent. But with something like this, where we can look at all the data at once, we can start to better identify and pinpoint what those differences might be attributed to. And so with this, 83% of the variability can be explained using just two variables or components. So we can use clusters and groupings from a score plot like this to pinpoint the potential sources to our springs. For example, we see that Giffen, Phantom Lake, and San Solomon cluster really closely with the Capitan Reef Aquifer. East Sandia, West Sandia, and the Pecos Valley alluvium also cluster quite nicely. We also notice that the Edwards-Trinity and the Capitan Reef also cluster, which may be indicative of the potential for mixing from source rocks. And we also notice that there's this outlier, this subset of samples from Giffen, Phantom Lake, and San Solomon. And so this is helpful because we can also start to identify what special events might be happening that we're capturing in our geochemical data. And so this subset of Giffen, Phantom Lake, and San Solomon can be attributed to the rain event signal that we capture at that time. And so by employing a PCA or using a tool like this, we are able to notice all these differences in just one step. And so this one step might be really easy, but it's driven by multiple sampling endeavors or campaigns, numerous historical, or data collection from all different sources. So don't want to undermine this being just one step, but rather it's just an effective way at seeing everything all at once. So I mentioned earlier that there still remain some uncertainties that we are trying to better understand. And one of those has to do with something called the strontium isotopes. And strontium isotopes can be really helpful in pinpointing or defining a source for your waters. So it captures the signal from the source rock, and as it moves through the system, it retains that signal. That isotope doesn't change as it flows through the system. And so we have a number of aquifers or potential sources in our area. We have the Capitan Reef, we have the Edwards-Trinity, the Rustler, and the Wild Horse Flat. And most of our source rocks would have an expected signal, or typically have a signal that is at this red line and below. So everything below the red line is what we might expect for the source rocks in our region. But as you can see, our Edwards-Trinity samples and our Capitan Reef and San Solomon spring samples are much higher than what we might expect for this kind of tracer in our area. And so a lot of people in the past, previous studies, attributed this signal to coming from Van Horn, specifically the Wild Horse Flat. And so what we've done here is through, again, analyzing or collecting for robust geochemical data over a broad spatial area, we've been able to further define that strontium signal that was originally thought to come from the Wild Horse Flat can be linked to the Capitan Reef or the Edwards-Trinity. So again, we've used a lot of different data, a lot of different plots over a long period of time, and what we've ended up with is being able to crystallize the conceptual model, or what we think is going on for San Solomon. Specifically, we think that the Capitan Reef and Edwards-Trinity waters mix to provide the majority of flow to San Solomon. So these structural features here, this main flow path, is where we think most of the water at San Solomon is coming from. We've used other things like carbon isotopes and nitrate and other tracers to be able to identify that recirculation and upwelling provide an additional source of recharge to East and West Sandia Springs. You might recall the PCA plot where we saw those rain events that stood out. We also think rain events provide local recharge to the springs, where they are able to seep into these Cretaceous outcrops and flow along the main flow path to ultimately feed to San Solomon. And so by collecting these new robust data, filling in data gaps, we've been able to come up with a refined conceptualization of what's going on at San Solomon. And I want to point out that this is not groundbreaking. If anything, it's more confirmatory, but it still helps us move the needle in better understanding what is contributing or recharging these iconic springs. Okay, so I mentioned that we are looking at all these springs in West Texas, so now we're going to move further east to Ties District and take a closer look at Diamond Y, Euphrasia, and Carges Springs, as well as Comanche Springs. So again, this is what the office looks like out in Fort Stockton. Here we have Euphrasia, Diamond Y, Carges, and Comanche. So again, we can use the same approach, the same PCA run to analyze our data from Fort Stockton. Similar to San Solomon, our major ions drive our first component, whereas strontium isotopes are help to explain variability in our second component. And so 92% of the variability in this data set is explained using just these two components. So it's, again, a really effective way to see the big picture in one step. There are differences in clusters that are apparent by this kind of score plot. We see that our Edwards-Trinity wells group together quite nicely, as do the Rustler aquifer samples we collected. And you'll notice that Comanche is right in between. It's sort of intermediate between the Rustler and the Edwards-Trinity. And so it makes us think that there may be a connection between the Rustler and the Edwards-Trinity that we can explore further down the line. And so this connection is made apparent by this plot. And moreover, Diamond Y, Euphrasia, and Carges Springs are not within that same, they're not within this cluster. They're separate from the rest of our samples, which will be important later. So to explore that connection, the possibility for mixing with Edwards and Rustler, we might take a closer look at some of our major ions, which is, in this case, chloride and sulfate. So this is just a graph of sulfate and chloride for our samples. And so, again, we see that there are some differences that are readily apparent. For example, our Edwards-Trinity wells tend to increase with chloride and sulfate in a linear way. As our waters become more brackish, we see an increase with sulfate and chloride. However, with the Rustler, as our sulfate increases, our chloride doesn't really change. So we see this sort of vertical change in these ion concentrations for the Rustler aquifer. But what's important is that Comanche is sort of right in the middle of these clusters. So for Comanche, it's pulled vertically. You know, the sulfate concentration for Comanche is pulled up more than we would expect if it was just Edwards-Trinity waters, pulled in the direction of those Rustler values that we see. And so we think this is a connection or further evidence for the mixing between the Rustler and the Edwards-Trinity for Comanche Spring. And again, our Diamond Y, Euphrasia, and Carges Springs are very different, have much higher TDS and sulfate and chloride concentrations compared to the rest of our samples. We can take it a step further and look at the strontium isotopes for this spring system as well. So as we see, again, similarly, our Edwards-Trinity waters have very similar strontium isotope concentrations. The Rustler signal is much lower, and unsurprisingly, Comanche is again right in the middle. So we see this consistent trend where Comanche is intermediate between our Edwards and our Rustler waters. So again, does that provide evidence for mixing of these two aquifer systems? We seem to think so. And again, our Diamond Y, Euphrasia, and Cargis springs is sort of clustered together as well and don't fall within that mixing line we would expect. So again, we employ all these geochemical and statistical analyses, and again, there's a lot more that we've done, but for the sake of this meeting, we've shown just a few examples of how we can sort of make connections between different aquifers and sources for our springs. So the conceptual model we think we think the conceptual model for Comanche is as follows. Here's Comanche and Fort Stockton. And so Edwards-Trinity and Rustler waters provide base flow to Comanche Springs. And the mechanism through which that's happening is where the Rustler aquifer is upwelling to provide that mixing to ultimately end up at Comanche. But why don't Diamond Y and the other springs fit in? There have been a lot of studies that have thought that, or ascertained that the Rustler is an important source for these other springs, but why aren't we seeing that same connection for Diamond Y, Euphrasia, and Cargis? I'll bring you back to the two plots we just saw before. We have elevated chloride and sulfate for Diamond Y and Euphrasia, as well as this, we also don't see a diluted strontium isotope signal for the Rustler. And so in short, the Rustler may be a source to Diamond Y and Euphrasia and Cargis, but it's likely not these Rustler waters because it doesn't give enough of a signal to provide that for Diamond Y. You know, why don't we, if Diamond Y was a source by the Edwards-Trinity and the Rustler, we might expect it to be more in line with Comanche, but we just don't see that. And so whatever that source might be, we haven't sampled it, and I hope that this is kind of the things we're thinking about moving forward to pinpoint what might be providing for this different signature that we see at these other springs. So again, there's been a lot of work done by us on the geochemistry and others, but also what's important is the structural work that's being done. And so this is just an image from a past report about 10 years ago of the structure, the faulting that was understood at the time for Fort Stockton and surrounding areas for the Rustler Aquifer. And others, namely LRE Water, have been working hard to better understand the structure that may provide for the Diamond Y character that we see. You know, that now that we have a much more detailed image of what the structure is out there, we hope that it might be able to pinpoint what that source to those springs might be. So questions for the future that I want to leave y'all with. What is the source for the high strontium that we see in both of our hydrologic systems? If it is the Wild Horse Flat for San Solomon, how is all that water getting to the springs? How is there enough water getting to the springs to provide that signal? Or is there another source? I'm not sure. Why doesn't the Rustler chemistry align with the source water for Diamond Y? And what additional chemistry can we collect to better understand these hydrologic systems? Where are there data gaps, temporal gaps? Where can we better fill in these gaps to answer some of these other questions? So in summary, springs in West Texas have complex and hydraulics and political boundaries. And today we've presented an approach to deal with some of these complexities. Namely, we've used a geochemical framework to better understand the sources of recharge that feed these complex spring systems out in West Texas. And so what I hope you take away from this is that this is a success story of what we can do when all of us work together, when we have buy-in from the districts, the GMAs, the research groups, the landowners. This is the kind of work that we can do. And so as we learn more, We hope to identify new ways to protect our springs in West Texas and beyond. And with that, thank you for listening, and I'd be happy to answer any questions.
Rebecca, is there a way to use the geochemical data and what you've done to quantify more the volumes and where they're coming from so that we can back calculate, how pumping or other impacts might, influence?
Sure. So the geochemistry can provide insight on sort of the relative contributions of different sources, right? 50% might be coming from here, X amount might be coming from here. And so when you use a conceptual model like that, you can let that drive your numerical model development to come up with those numbers that you allude to. So they go hand in hand, and the chemistry just can help with the development of more quantitative methods to come up with answers like that.
The areas that we collected rustler water from, were those predominantly from the Belgian area, or did you have some more rustler data further to the northwest?
I'll show you if I can get there. Oh. Or maybe. So these are the samples we've collected as part of our work out west. And the blue squares are Edwards-Trinity, and the orange squares are our Rustler aquifer samples. And so you'll notice that we have 2 Rustler aquifer samples from Leon Belding. And we also have one from further north, down gradient from Comanche, near the springs. And so these Rustler waters, particularly this one up north, has a very different chemistry than these springs. And so that's what we've captured so far. We tried to get other Rustler samples, but they're just very limited in this area. But I hope that those are the kind of data gaps that we can fill in moving forward so we can better understand the connection of the Rustler, between the Rustler and these springs.
So at this point, where do you believe that the water for St. Solomon Springs originates, and how old is it? How long has it been in flow to the springs?
I'll show you. So we think that the waters for San Solomon originate in Culberson County in this northwest, sort of northeast oriented flow path. These waters are about 15 to 20,000 years old, and that's the signal that we capture in Balmorhea at the springs. So this is what we believe to be a really important feature and the main flow path for where these waters come from. Does that answer?
Yeah, so from the Apaches and the fault zone on the
correct. There's this large structural feature here called the Stocks Fault. And there are these northwest and southeast oriented faults that essentially allow that water to upflow and feed and ultimately make these springs in Balmorhea.
Thank you.
I didn't catch that. Did you say thousands or hundreds?
For the age?
Yeah.
Between 15 and 20,000.
Okay. All right. And then the faults, do they have anything to do with the Alcone system or just different?
That's a good question. I don't know.
Rebecca, so based on this, Matt Juliana's theory was, and Jack's was that it was coming out of the Wild Horse Flats. You think the chemistry is significant enough difference between, it's not a mixing thing where you've got Wild Horse Flat water contributing to the Capitan Reef and then you're kind of all seeing the same thing through there?
I'm really glad you asked. So we think that we cannot exclude the Wild Horse Flat, right? But what we can't explain is how the the physical hydrology suggests that there's just not enough water coming from the Wild Horse Flat to feed what are these large springs in Balmorhea. So Matt and others attributed that strontium signal to the Wild Horse Flat. Where else do you get this really high strontium that you see in the springs? So we don't know the extent of the contribution from the Wild Horse Flat, but there has to be something else that conveys that much water, something else that can provide for how much spring flow we see. So I don't want to exclude or say that the Wild Horse Flat is not an important part or a significant part, but I also can't say that it is. So that's again, where is this high strontium coming from? They pinpointed it to the Wild Horse Flat, but is there something else that, we've linked it to the Capitan based on our sampling. We know that we can get that signal from the Capitan Reef. So hopefully, we tried sampling in Van Horn and the Wild Horse Flat. We were not successful, and I hope that others can fill in that data gap moving forward so that we have a better idea of that.
Thank you.
I've never been there, but I was just at the spring, and Balmorhea.
Balmorhea?
Incredible place. And the sign says it comes from Wild Horse Flat, but it calls it a salt flat. I've never been to Wild Horse. Is that a salt pan?
Correct.
See, I would rule that out right away, because you don't have, fresh water and salt water do not mix under the ground. They do at the surface, but not under the ground. And any water that was in that flatwood would become saline, because at the surface it mixes.
Right.
And so the fact that it's fresh water, I would just sort of trivially reject it anyway. Or if it's a source, it's a very small pollutant.
Sure. Yeah, these springs are pretty brackish. They're on the order of 2,500 TDS. Don't. No, but you bring up a good point, because back to your question, the chemistry at Wild Horse Flat is also very different. It's very low TDS, and it just can't provide that signal based on the major chemistry as well as isotopes. And so,
I mean, it's being 10,000 TDS. I taste water inadvertently when I'm swimming in it. And I was snorkeling in it yesterday. It seemed like it was less than 10. You're saying it's 1,000?
no, 2,500.
2,500. Okay, it seemed like 2,500.
Correct.
I would totally rule out Wild Horse Flat just based on that. I mean, I would, if we'd be making a contribution, it would have to be significantly diluted.
Right.
I was the sign's wrong at Balmorhea, and I would rule it out.
Well, that's part of why we're continuing this work out west, and we're continuing to sample so that we better understand what is going on. There was a good basis for attributing spring flows to Wild Horse Flat, because strontium isotopes, among other things, pointed to it. And so as we've collected more over the years, we've been able to really showcase the importance of this regional flow path from the Apache Mountains and the Capitan Reef to provide for spring flow. And again, I don't want to take credit for all of that, because this work has been built upon a lot of other studies that have ascertained the importance of the Capitan Reef and the Apache Mountains. And the work we've done has been confirmatory and really just nailed it down, even though there's still a lot more work I think that should be done. So I appreciate your insight.
I'd like to add one more thing. Getting away from looking back at the politics of this and trying to protect and manage these springs. We're looking at water coming out in Reeves County that crosses through Jeff Davis County that supposedly comes from Culberson County. And we're looking at different ground management areas, different counties, different regional planning area, everything. So it's a convoluted mess trying to be on top of it and protect them, and everybody get together and do something, as much research as we can to ensure that they'll hopefully keep flowing.
But it's events like these that bring awareness to those kinds of things. And so when you have landowners and others in the community that believe in what you're doing and the mission of these GCDs and the work out west, it really empowers you to be able to work with others. And so I didn't say this, but thank you so much to Greg and Amber and Rob for the opportunity to be here and be a speaker, because this is just high caliber event and I'm so honored to be a part of it. So thank you.
Come back so it'll start raining.